Thank you for viewing this talk. In this talk, I provide specific predictions for new elementary particles. Moreover, I discuss how those particles could account for known phenomena. I discuss possible answers for each of these questions. What elementary particles might people find? What is dark matter? What is dark energy? What causes the so-called rate of expansion of the universe to change? My work correlates solutions to equations involving isotropic pairs of isotropic quantum harmonic oscillators with elementary particles and some properties and interactions associated with such particles. A subset of solutions correlates with all elementary particles known as of 2015. Other solutions correlate with possible elementary particles. The periodic table for elements provides a possible parallel. For some decades, the periodic table provided concepts for what elements might exist. Later physics provided concepts regarding how nature, in effect, chooses isotopes. My work points to what elementary particles might exist. The work does not necessarily include a model for how nature chooses particles. My work points to possible how for phenomena to which particles contribute. The spin, S, provides an index for a catalog of elementary particles. So does sigma, which is +1 for free-ranging particles and -1 for non-free-ranging particles. In addition, M denotes rest mass. I predict up to 11 families of elementary particles. For each subfamily for which S appears in italic font, people have found all the particles. For subfamilies for which S appears in bold font, people have yet to find any particles. The chart shows free-ranging particles in rows above rows that show non-free-ranging particles. For non-free-ranging particles, I identify symmetries that combine to provide Poincare group symmetry, or special relativity symmetry, for composite particles. For non-zero mass elementary bosons, people have found all the free-ranging particles and none of the possible non-free-ranging particles. A formula involving an integer, n, approximately links squares of masses. The 202 and 201 bosons could have charges of plus and minus 1/3 the charge of a positron. In the early universe, these bosons could convert antimatter quarks to matter quarks. Such conversions could be key to nature's establishing the matter-antimatter asymmetry, or baryon asymmetry, people observe. A possible minimum energy to produce these bosons is at least 532 GeV, in that, likely, production of non-free-ranging elementary bosons involves producing at least pairs or triplets. To the extent that nature includes spin 3/2 elementary fermions, the number of generations is possibly 15. Possibly, an algebraic formula links the ratio of the mass of a tauon to the mass of an electron to the ratio of, for two electrons, electromagnetic repulsion to gravitational attraction. If so, I predict a tauon mass that is more accurate than particle data group year 2014 experimental results. Experimentally determining an adequately accurate tauon mass could lead to predicting the gravitational constant to more accuracy than people have determined. The work points to a concept for interaction vertices of conservation of fermion generation. Apparently, gravitons would not produce neutrino oscillations, but other particles would. Thus, as a previous slide shows, neutrinos possibly could have zero mass. The work estimates a range for the weak interaction. The G family provides for all zero-mass free-ranging elementary bosons. Only two such bosons, the photon and the graviton, correlate in the sense of traditional physics with 1 over r squared forces. The spatial dependence for the force associated with one boson is r to the minus 8 power. The other forces correlate with r to the minus 6 and r to the minus 4. For the largest objects of which people know, the r to the minus 8 force drove the Big Bang and a few billion years of accelerating expansion of the universe. Then, r to the minus 6 forces provided for a few billion years of decelerating expansion. Then, r to the minus 4 forces provided for the recent few billion years of accelerating expansion. Smaller objects have transited into a fourth era in which gravity and electromagnetism provide the most significant long-range effects. I just discussed one use people make of the term dark energy. People also use the term to discuss the stuff that contributes more than 2/3 of the observed density of the universe. A mathematical symmetry points to the possibility that nature includes 48 instances of photons and all non-G family elementary particles. If so, 8 instances of gravitons exist, and each instance of gravitons correlates with 6 of the 48 instances I just mentioned. An observed ratio of densities is about 5.3 dark matter to 1 ordinary matter. If the symmetry pertains to nature, dark matter could consist of 5 instances of extended standard model particles and the ordinary matter-related instance of some of the extended standard model particles I predict. If the symmetry does not pertain to nature, dark matter could consist of just the ordinary matter-related instance of some of the extended standard model particles I predict. Dark energy stuff might consist of the other 42 instances, or, in effect, 7 copies of ordinary matter plus 5 instances of dark matter. I think this result can be consistent with observations. Other aspects of the work may provide insight regarding dark matter galaxies, mechanisms leading some black holes to form quasars, and other phenomena. Opportunities exist to check, improve, extend, and use the theoretical work. To the extent some of the work might pertain to nature, opportunities exist for experimental, observational, and inferential work. The book, Models for Physics of the Very Small and Very Large, provides more information. Springer published the book. Springer and Amazon carry it. The web link provides, for example, pointers to the book and to no-cost downloads that Springer makes available. Thank you for viewing this presentation. I welcome discussion.